In this video, we're going to continue making changes to our linked list driver, adding some additional functions. We have functions to add to the linked list, so now let's add some functions to remove. So before we actually start writing the function, let's review what we need to do to delete from the front. The head is pointing to the node we want to delete. So to remove that node from the list itself, we just need to set the head equal to that node we're going to delete's next element. That will be the second node in the list. That's the new head. And then this will be garbage collected later. And before we do all this, we definitely need to make sure that we remove any pieces we need from this node, which in this case would be the element. So let's add our new function. We're going to return a generic object, depending on what type is stored in the list. And we'll call this function RemoveFirst. So the first thing we're going to do is check if the list is empty. If the list is empty, then we obviously can't remove anything from the list. So we're going to throw a no such element exception. And then if it's not empty, then we're going to get the element from the head node. Then we're going to set the head of the linked list to the old head's next element. Now, before we do that, we're going to get a reference to the existing head just so we can do some things with it later. And we'll say that head is equal to head next. This is where we actually set the new head. Then I'm going to clear the references in the old head node, just in case somehow somebody has a reference to that actual node. This will prevent anybody with a reference to the old head from accessing either the element or the rest of the list from that node. So we'll say old head element is null. And we'll also say old head next is null. So now that reference, even if a reference exists out there, we're going to still set those to null so that nobody can do anything with them. So now we removed something from the list. We need to decrement the size, and we're going to return the old head's element. And one other thing we want to do, if the list is empty, we're going to want to set the tail equal to null, because the tail should be null if the list is empty. And the reason for this, and you may say, well, why are we checking to see if the list is empty twice? Well, here we're checking, is it empty before we remove an element? Here we've removed an element and we're asking, is it empty now? Because now we're removing from the front. So we need to, if we remove from the front, that might be the last element. If it is, the tail also needs to be null. It doesn't need to be this old head. So that's our RemoveFirst method. So now let's add RemoveTheLast method. And that'll actually be a little more involved. So let's first see what we need to do. When we're going to delete that last node, the tail points to that. So there's two things we need to do. We need to find this node that's the second to last node. And we'll have to actually do that starting with the head, going to the next node, until the next node is the tail. So we're going to iterate through the list looking for the node that's right before the tail. Once we find that node, we set its next equal to null, and then we set the tail equal to that new node. So let's see how that's going to look in code. Now, just like before, if the list is empty, I'm going to throw an exception. So I'll copy and paste that exact code with RemoveLast. So now I've established that it's not empty, so I need to go ahead and get the element from the tail node. This time it's really bothering me that I have this error here, and that's because I haven't returned anything. So I'm going to return ret, and that'll take care of that error. But of course, we have a lot more work that we need to do before we actually return. We do have an easier case, and this is sort of like when we added to the rear. I think we did something similar. If the size of the list is equal to 1, that's actually an easy case. we can just remove the first. Because if there's only one element, that last element is also the first element. So that takes care of our case anytime we're dealing with like an empty list after we remove and that sort of thing. All of that's handled in remove first, so we don't need to worry about it. We only are going to use remove last if there's at least 2 elements in the linked list. So if the size is not equal to 1, the first thing we do is we need to find the node that's going to be the new tail. And I need to put an else here. So the way we're going to do that, we're going to say that the new tail is equal to the head. And you may think, well, hey, that's not right. It should be the one before the tail. Well, that's actually just where we're going to start looking. So then we're going to have a while loop. And while new tail next is not equal to the tail, we're going to set new tail equal to new tail next. And when this loop completes, new tail will be pointing to the node right before the tail, because you'll notice as soon as its next is equal to the tail, the while loop executes. So now we can say at this point, new tail is referring to next to last node. Now, just like we did above when we removed from the front, we're going to clear the old tail. And the way we do this is we're going to get a list node reference. We'll say that that's equal to the tail. And we've actually already got the tail element here, so we don't need to do that again. And then we set old tail's element equal to null. And then we're going to set the tail to the new tail. So the tail is going to be new tail. Tail.next is going to be equal to null, since this was pointing to the old tail. And the size we're going to decrement. Now you may say, why don't we need to check to see if the list is empty now? Well, because it won't be empty because there's at least 2 elements in the list if we're going to execute this code. If there's only 1 element in the list, remember up here we call remove first. So there's probably some things actually looking at this that we could probably do to simplify the code a little bit. It turns out we don't really need this. We could just actually say tail element is equal to null and tail next is equal to null. But I think by using this variable, it's a little more clear what we're doing. So we'll leave that there. So let's go to our driver and let's test this code. So we'll say the front is equal to my list remove first, and rear is equal to my list remove last. So we removed some things here, and why is that giving us an error? Let's take these 3 lines and let's print them again once we've actually removed the things from the list. And let's say system out print line, and then we'll say old front, and we'll do the same thing for the rear. And then we'll check that the rear, the first, and the last are correct. And then we'll also print the current list. And actually, let's do this here. So it's a little bit earlier. And I think that should test both of those sufficiently. So as we run this, so we had hello world Chandler Gilbert. The old front was hello. The old rear was Gilbert. Now we just have world and Chandler. The size is 2, and first and last worked. And you'll notice even though we tested those same methods above, now we're testing it to see, hey, do those still work once we've removed some elements from our list? So now let's write some methods to check to see if things are actually in the list. So the first one of those we'll write is a contains method, and that's going to return a Boolean whether or not a certain value is in the list. So in order to check if a linked list contains a certain element, we're going to have to traverse the list, checking each node to see if the element is there. And we did this with our remove rear. Here we're going to have a current reference, and we'll start at the head. And while current is not equal to null, and there's another case, we also want to make sure that we haven't found what we're looking for. So we'll stop either at the end of the list or once we found it. And of course, if we get to the end of the list and haven't found it, then found will be false. So we're going to say that found is equal to current element equals the value we're looking for. So this checks if the current node holds the element. And maybe I should put that above it like that. I think that's a little better. And then we'll say that current is equal to current.next. And you may say, well, why are we going to change that if we found it? Well, we don't really care about current. This is what we actually care about in this case. So the fact that we're changing current after that variable doesn't really make a big difference. And so once we've done this loop, we're going to return whether we found it or not. And that'll give us a Boolean asking, is a certain value stored in the linked list? Another function we might wish to have would be something that says, hey, not only is it in the list, but where is it in the list? And so we can write a method called IndexOf, and that particular function is going to return the index where the value is stored. Now, if the value isn't stored in the list anywhere, we're going to return -1. And so that's why we're going to initialize our return variable to index -1. Now, the other variable we're going to need is something to keep track of the index, because each node doesn't have an index. Although it is possible to write a linked list with an index, but that's not something that we're going to deal with here. So we're going to traverse the list, checking each node, just like we did with contains. So we'll say list node current is equal to the head, because that's where we want to start. And while current is not equal to null, you may say, well, why aren't we checking for found here? And I'll show you why in a moment. We're going to have a different approach here. So while current's not equal to null, meaning this loop is going to go until it reaches the end of the list. And let's finish the traversal part. Current's going to be current.next, and we're going to need to increment index. So this is going to go through the entire list, giving us the index where different values are stored in the linked list. And of course, a linked list doesn't have an index, but in this case, we're saying it's stored in the 5th node, or the 1st node, or the 7th node. So at each node, we're going to compare to see if we have what we're looking for. So current's element, is that equal to the value we're looking for? And if it is, we're going to set our return value to the index. Now, if I leave this as is, it'll go through the entire list, even if it finds it, and also it will return the index of the last appearance of that element in the list, and we probably want the first appearance of the element in the list in the case of duplicates. So I could add a found variable like I had with contains, but here let's do something a little different. Let's call break. And what break does is it says, get me out of this loop. So once I find something that equals the value, I'm going to exit, and that's going to be the end of this loop, and I'll return whatever that index was where I found what I'm looking for. So I think that completes the methods we want to do in this linked list class, although we still need to do the iterator. We'll do that in a different video. Let me just go through. So we have a toString, we have first and last, we have size, we have is empty, we have index of, we have contains, We have remove last. So I think, yeah, that all looks good. And then we have remove first, add to rear, add to front, and our constructors. The code is available on the GitHub site, so if you want access to it there it is. Let's go ahead and test these new methods that we've written. So what I'm going to do is I'm going to create an array with some values in the array. And so here I have something that appears, actually let's find each thing that is in the array just to make sure that that works. So I'll add hello world, and another string that's not going to be in there is Arizona. Okay, so here, this is going to be my array of search values. And then I'm going to go through that array, and if my list contains that value, then my list contains, and we'll say val, at index of that value. And if it doesn't contain that, then we'll say my list does not contain val, and then we'll say whatever the index result is equal to this. And this should be -1 if you'll remember how index of runs. So let's run this, and it looks like, oh yeah, we removed hello. So let's do this. Let's move this test array, and then let's copy all this code. So we have 9 lines, and I'm going to do the contains testing for the entire list, and then after I've removed it. So I think that'll be interesting to see the results. So here you can see it did find world, and it did find Chandler, but it didn't find any of the other strings. Whereas here it did find hello, world, Chandler, but it didn't find CGCC. Okay, so that looks good. And you'll notice that we tested values that are all over the string. Now, I removed some of the stuff here, but now I'm going to remove the rest of the stuff. So I'm going to copy that same code. Front and rear are already defined, so I can keep using this. And so now I've removed everything. So let's see. And I have an exception because, let's see, I have a empty linked list exception in the driver at line 72. So of course this is going to be an exception because the list is empty. So actually that works the way I want, but I'm going to go ahead and just take those out because the list is empty. To finish up, now I've added nodes. I removed all the nodes. Notice there are no nodes here. The size is 0 and so forth. So now, to finish up, I'm going to add to the front V, and I'm going to add to the rear end. Let me print first and last just to be sure those are still good. So I guess instead of deleting them, I should have moved them down here. So there we go. I'm printing the first and last, and then I'll print out the list as well. So if I run this code, you can see when I finish up, everything looks good. Let me just make sure that, I don't know why I don't have the size here. So let's put that there. My size is 2. So again, one of the things you always want to test when you're doing linked data structures is when I add things to the data structure, remove everything, Now it's empty. Can I add more things and it still work? And it looks like that's the case here. So this was a pretty thorough test of this. So hopefully we thought of all the cases. It's very easy to run into a null reference exception and that sort of thing when you're working with linked structures, but I think we have this pretty solid. So the only thing left for us to do is to create the iterator, and we will do that in a different video.